All right, for the second part, we're going to look at some other types of area between two curves problems. So we'll look at those different styles. There's a little wrinkle to them. All right, so if I want to find the area enclosed between the curves, these are x equals curves. So that means that if I graph them, it would be y squared is a sideways parabola. So it looks like this. And x equals y plus 2 is the same thing as y equals x minus 2. So we have an x-intercept of -2, and it's this line here. Oh, and then enclosed between those two curves and the x-axis. So we're looking at this region right here. Here's a more professional graph of that. So what I notice here is that we don't have one curve on top of the other. We have curves that one curve is to the right of the other. So if I draw rectangles, my rectangles are going to go sideways. And I'd still like to add up infinitely many of them, but I'm going to look at my rectangles oriented this way. The height of my rectangle is going to be a little tiny change in a y coordinate. And the width of my rectangle is going to be this x-coordinate minus this x-coordinate. So it's going to be the further right function, which is y plus 2, minus the further left function, which is y squared. And so when I add up all of those infinitely many little rectangles, the area would be y plus 2 minus y squared times dy. And then the limits of integration, we're going to start at 0 because they told us x-axis, and we're going to stop where they cross. So that would be y squared is equal to y plus 2. And the y equals -1 was the one that was down here, but we don't want that one. We want to go from 0 to 2. And then we would do antiderivatives. Oops, minus y cubed over 3. And we do that integral from 0 to 2. So 4 halves, which is 2, plus 4 minus 8 thirds. And I'm not going to go any further than that because I can always just let the arithmetic go. We're going to have one last wrinkle in our last example. If I want to find the area of this shaded region, I notice that these are not x equals functions, but they are, like, it would make sense almost to draw a rectangle sideways, except that these are not functions that easily fit that pattern. So we're not going to do that, but what we can do instead, if there's no function that is taller than the other, then we can say, well, we're going to draw our rectangles, and our rectangles here are going to go from 0 to y equals x. And then when we get to this point, our rectangles are going to go from 0 to x minus 6 squared. So if I want to find this area, I'm going to break it into two separate integrals. I'm going to go from 0 to 4, and I'm going to use the x curve. And then I'm going to do an integral from 4 to 6, and I'm going to use the x minus 6 squared curve. I really recommend, as you're doing these problems, that you draw the rectangle in place and take a look at what you're doing with your rectangles. Once I started drawing rectangles, it was clear that I was doing the integral of just one curve at a time as I was doing these rectangles, as I was doing this area. All right, that is area in the plane using all sorts of different curves.